Will humanity ever truly become a cosmic civilization? Have you ever imagined a future where our civilization could harness the entire energy output of planet Earth, and perhaps one day even command the power of stars and entire galaxies? Our theme for this deep dive is the Kardashev scale. This is a unique measure that charts the evolutionary stage of a civilization in the universe by its energy consumption back in the 1960s, when the space race was intensely heating up. A Soviet astronomer named Nikolai Kardashev proposed this scale. He believed that a more advanced civilization would inevitably require a tremendous amount of energy. And from that standpoint, he attempted to search for extraterrestrial civilizations. In this video, we will use the Kardashev scale as our guide to thoroughly explain the current position and the future vision of human civilization. Let's embark on this grand journey into futurology together. Although humanity has advanced its technology by leaps and bounds in just 100 years, on a cosmic scale, we are still nothing more than inexperienced youths. So, can we, these youths, one day evolve into a super civilization capable of controlling even galaxies? The Kardashev scale gives us a hint. First, let's explore the fundamentals of what this scale itself signifies. What is the Kardashev scale? The Kardashev scale is a measure of a civilization's. What is the Kardashev scale? It is a scale that indicates the level of development by the amount of energy used. It was proposed by Kardashev in a paper in 1964 and was originally an idea for searching for extraterrestrial civilizations. Space civilizations. There may be other civilizations in the universe besides us. However, in order to search for the signals they emit, it is necessary to consider how much energy the civilization is using. Here, Kardashev classified civilizations into 3 types. The groundbreaking point is that he measured them not by the scale or culture of civilization, but by the universal measure of energy. So what are those 3 types? Specifically, Type 1 civilization. A planetary civilization. A civilization that masters all the energy available on one entire planet. In short, it is the stage where they can use and control the energy produced by their own mother star, such as sunlight, atmosphere, ocean, wind power, and geothermal heat, without leaving anything out. Type 2 civilization. A stellar civilization. A civilization that completely dominates the energy in one star system, to the level of utilizing the entire energy of their own sun. It is even envisioned that they could enclose the star's energy with a huge structure like a Dyson sphere. Type 3 civilization. A galactic civilization. A civilization that can control all the energy that exists in one galaxy. It is the stage where they can handle the vast energy sources of all the hundreds of billions of stars in the galaxy, or even the black hole at the center of the galaxy, as they please. These 3 stages correspond to the expansion of scale of planet, star, and galaxy, and they pose the question of how far human civilization can expand its energy. The digits of energy consumption are also orders of magnitude different, with a dramatic increase of about 10 billion times from Type 1 to 2, and another 10 billion times or more from 2 to 3. The estimated output of a Type 2 civilization is about 10 to the 26th watts, and for a Type 3, it reaches 10 to the 37th watts. The idea of measuring civilization through the lens of energy was novel, but for that very reason. It may be possible to verify it through observation. For example, it is thought that for a Type 2 civilization, the characteristics of the light emitted by its star would change. And for a Type 3 civilization, abnormal infrared rays would be observed throughout the entire galaxy. The Kardashev scale was not just a thought experiment. It has had a great influence on science fiction writers and scientists, and has also stimulated our own thinking about our future energy vision. Thus, the overall picture of the Kardashev scale has come into view. So, where does the crucial human civilization currently stand on this scale? In the next chapter, let's explore the current position of us humans and the challenges we face. Where does humanity stand now? When you hear about Type 1, Type 2, and Type 3 on the Kardashev scale, it makes you wonder, where does humanity currently rank? To get straight to the point, we as a species have not yet even reached the level of a Type 1 civilization. Numerically, this means we are at a type 0.x, with experts estimating our position to be around 0.7. The American astronomer Carl Sagan proposed a formula to calculate a civilization's energy usage on a continuous scale. And according to his calculations, humanity was at about 0.7 back in the 1970s. In fact, in the early 2020s, the world's total annual energy consumption has reached about 600 exajoules, which is equivalent to 18 to 19 terawatts. Applying this to Sagan's scale, we land at around 0.73. This is not even a few percent of the approximately 10 to the 16th power watts required for a Type 1 civilization. It's less than 1%. Specifically, we are only meeting about a few tenths of a percent of that requirement. To put it another way, it calculates out that humanity is using less than 1/1000th of the solar energy that our Mother Earth receives from the Sun. The road to becoming a true spacefaring civilization still feels very, very long. So, what kind of energy sources is the world actually using to supply those 18 terawatts? When we take a broad look at our current energy situation, a clear picture emerges of our heavy dependence on fossil fuels, oil, coal, and natural gas. As of 2022, about 80% of humanity's energy supply still comes from these fossil fuels. Renewable energy sources like solar, wind, and hydropower have been growing rapidly in recent years, but their share of the total still hasn't reached 20%. Furthermore, energy demand itself continues to increase at an average annual rate of 1 to 2%, painting a picture of an energy-hungry human race. What this situation implies is clear. For humanity to approach a Type 1 civilization, a civilization that utilizes energy on a planetary scale, we must dramatically expand our energy supply. But at the same time, the fossil fuels that are currently our main source are a finite resource, and their excessive use brings about the serious side effect of climate change. In fact, over the last few years, we've seen a succession of extreme weather events around the world, like record-breaking high temperatures, massive typhoons, and wildfires, making the effects of climate change something we can feel on a personal level. The carbon dioxide emitted from the mass consumption of fossil fuels reaches about 36 to 37 billion tons annually, increasing greenhouse gases on a global scale. If things continue on this path, the Earth's environment itself could become the very barrier that prevents humanity's development. In fact, scientists are warning that if we continue on this path, climate change, environmental destruction, and resource depletion could become the tipping point where our civilization becomes unsustainable. In other words, a great filter in terms of the Kardashev scale. This means there's a risk that our civilization could self-destruct before it even reaches Type 1. On top of that, human society is piled high with social challenges like poverty, inequality, and international conflicts over energy. If a war breaks out, the development of civilization becomes a secondary concern. Indeed, geopolitical tensions over energy resources remain a factor of instability in the world today. If we cannot overcome these internal problems, it will be difficult for humanity to come together as one and step up to Type 1. Even if we become technologically capable of increasing our energy supply, humanity is now at the 0.7 mark, just before Type 1. But we are also in a perilous stage that could be called a technological adolescence. Can we overcome this hurdle and evolve into a true planetary civilization? In the next chapter, we will consider the path to a Type 1 civilization and the technology and cooperation required to get there. The path to a Type 1 civilization. The path to civilization. What road must humanity travel to reach a Type 1 civilization? A civilization that controls energy on a planetary scale. The keys, undoubtedly, are dramatic advancements in energy technology and global cooperation. While the expansion of renewable energy and improvements in energy-saving technology are currently underway, approaching Type 1 status demands a breakthrough of an entirely different magnitude. Let's look at the specific points we can consider. First, on the technological front, the practical application of nuclear fusion energy is a major ambition. Nuclear fusion is the same principle that allows the sun to shine, a technology that releases enormous amounts of energy by fusing light atomic nuclei together. Unlike the current mainstream nuclear fission power generation, fusion is, in theory, a clean and virtually inexhaustible energy source. If we can achieve fusion, we will be able to extract a sun's worth of energy from hydrogen. According to some estimates, to obtain the output of a Type 1 civilization, we would need to completely convert approximately 0.1 kilograms of matter into energy every second. In light of Einstein's famous equation, E equals mc squared. This is a colossal amount. However, in the case of fusion, only about 0.7% of the mass is converted to energy, which means we would need to convert over 10 kilograms of hydrogen into helium every second. But Earth's seawater contains a virtually limitless supply of hydrogen suitable for fusion, meaning a truly astronomical amount of energy lies dormant. In recent years, research and development centered around projects like the International Thermonuclear Experimental Reactor, or ITER, in France, has been advancing the demonstration of fusion power. If fusion power plants can begin operating safely and at a commercial level, humanity's energy output will increase exponentially, bringing us significantly closer to Type 1. Next, an infrastructure that can distribute energy on a global scale is also crucial. For example, if a region where it is daytime and solar power is abundant could transmit electricity to a region where it is nighttime, overall energy efficiency would rise. To achieve this, we need a global power transmission network, a supergrid, and the establishment of high-capacity energy storage technologies that can save and transport energy. Advanced energy management by artificial intelligence will also be key. If an AI could optimize supply and demand forecasts in real time, we could utilize the energy we possess without waste. The very act of using our limited resources efficiently is a shortcut to Type 1. Furthermore, we must also consider obtaining energy not just from Earth, but from space. One area gaining attention is space-based solar power. On the ground, sunlight is affected by nighttime and weather. But in space, it shines down 24 hours a day. The concept involves deploying massive solar panels in orbit around the Earth and transmitting the power obtained to the ground using microwaves or other methods. This is also known as an orbital solar power satellite. And if realized, it could supply immense amounts of clean energy to the entire planet. Research is advancing in countries like Japan and the United States, and there have already been examples of successful small-scale experiments. Another possibility is the full utilization of geothermal energy and other energy sources the Earth naturally possesses. The heat from magma inside the Earth, geothermal energy, and the tidal power generated by the Moon's gravitational pull are also, in theory, enormous energy sources. To become a Type 1 civilization, we will likely need to master all of these renewable energy sources in an integrated way, no matter how far technology advances. The path to Type 1 will not open unless society as a whole accepts it and adopts a cooperative stance. Global energy management requires cooperation that transcends national borders. It demands the sharing of energy resources, the exchange of technical knowledge, and above all, a perspective that prioritizes the interests of all humanity. This is by no means an easy task for today's international community. There are economic disparities and differences in political systems among countries, and energy issues have at times created friction between nations. Nevertheless, the fact that a framework of cooperation, such as the Paris Agreement, has gradually been built in the face of our common enemy of climate change is a hopeful sign. Perhaps a future lies on this trajectory, where global citizens unite as one to overcome our energy problems. So, when exactly will humanity reach a Type 1 civilization? There are various theories on this. Optimistic scientists predict it could be achieved in the next 100 to 200 years. If technological innovations like renewable energy and nuclear fusion progress smoothly and social cooperation is also achieved, humanity might proudly join the ranks of planetary civilizations in the 22nd or 23rd century. On the other hand, under a scenario where energy consumption continues to grow at its current gradual pace, some estimates suggest it could take several thousand more years. For instance, a study in the year 2023 concluded that by the year 2060, humanity would only reach about a Type 0.74, and at the current pace, it would take several millennia to reach Type 1. In short, whether humanity can ascend to a Type 1 civilization depends on how much of a fundamental shift we can make in this century. The global challenges are immense, but the future that lies beyond them is incredibly compelling. If we can achieve a Type 1 civilization, we will see a world where humanity can control the climate and natural disasters, and where everyone on Earth can enjoy the energy they need. It's an image of the Earth itself becoming one giant power plant. Having reached that stage, humanity's next goal will be to venture beyond the solar system and become a civilization that controls its star, a Type 2 civilization. Next, let's turn our thoughts to the world of a Type 2 civilization. A civilization that commands the power of a star. Type 2 civilization, governing the power of a star. Type 2 civilization, mastering the power of a star. This stage, also known as a stellar civilization, describes a world far beyond human imagination. It's a civilization that literally controls the entire energy output of a star. And the quintessential concept representing this is the Dyson sphere. Here, we'll explore what a Type 2 civilization might look like, focusing on the Dyson sphere, and consider the technological and physical challenges involved. This is an artist's conception of a Dyson sphere, a massive structure completely enveloping a star. It is hypothesized that an advanced alien civilization would build such a structure to utilize the entirety of its star's energy. A Dyson sphere is a hypothetical megastructure built to surround a star, with the goal of capturing every bit of the energy it emits. It gets its name from American physicist Freeman Dyson, who first proposed the concept in 1960. When you think about it, the sunlight that reaches Earth is just a tiny fraction, only 1 part in a few billion of the sun's total energy output. This led to the bold idea that if you were to build a wall around a star, you could capture immensely more energy. The ultimate version of a Dyson sphere is a massive, solid shell that completely encloses the star. However, a more realistic approach is considered to be a Dyson swarm, which would consist of a vast number of satellites or rings orbiting the star. In either case, a Type 2 civilization is envisioned to construct such a megastructure, allowing it to harness nearly 100% of its parent star's energy output. Although the Dyson sphere might sound like an idea straight out of science fiction, it doesn't violate the laws of physics. This has led scientists to seriously search for evidence of civilizations that might have built one. The logic is simple. If a Dyson sphere exists somewhere in the universe, it would block the light of its star. In its place, we should be able to observe a massive amount of infrared radiation, which is essentially heat. Astronomers have been actively searching for stars that show unusual infrared emissions using data from infrared space telescopes. A famous example is KIC 8462852, also known as Tabby's star, which made headlines in 2015. This star exhibited strange and significant dips in its brightness, leading to widespread speculation that an alien civilization might be in the process of building a Dyson sphere, although the current leading theory suggests that this is a natural phenomenon caused by a swarm of comets. The debate around this alien megastructure captured the public's imagination. More recently, in the 2020s, a study reported the discovery of 7 stars that were potential Dyson sphere candidates. However, upon further review, it was suggested that these signals were likely noise from distant, dust-enshrouded galaxies. As of now, no definitive observational evidence for a Dyson sphere has been found. Even if we had the technology to build a Dyson sphere, the challenges would be truly astronomical. First, there's the issue of materials. It's been said that to create a sphere around our sun, we would need to dismantle planets like Mercury and Jupiter just to gather enough raw materials. Even if the materials could be gathered, we would face the wall of structural integrity. Is there any material that could withstand the intense heat, light, and particle radiation from the sun? Could we ensure the mechanical stability needed to maintain such a gigantic sphere? With our current knowledge, no known material could maintain a massive structure in close proximity to the sun. Realistically, a Dyson swarm a system of millions of independent mirrors or panels in orbit, seems more feasible than a solid shell. Still, it would require a mind-bogglingly complex control system to manage the orbits of millions or even billions of power-generating satellites. An even greater challenge is the heat problem. While a Dyson sphere would collect energy, it would also emit enormous amounts of waste heat as infrared radiation. The interior of the sphere would become incredibly hot. And without an effective cooling system, the structure itself could melt. The very act of collecting too much energy creates new technological hurdles. Furthermore, maintaining a Dyson sphere would require long-term maintenance and orbital corrections. A Type 2 civilization would likely need advanced artificial intelligence and self-replicating robots to carry out such a multi-generational project. It's possible that the civilization would have to act less like a collection of individuals and more like a single, unified organism, looking beyond stars. Another potential energy source for a Type 2 civilization is a black hole. While black holes themselves don't emit light, if you feed matter into one, it creates an intensely energetic accretion disk that radiates powerfully. In an extreme scenario, one could imagine a cosmic engine that disposes of unwanted matter by dropping it into a black hole and harnessing the energy released in the process. It's also theoretically possible, though we don't know if it's physically practical, to extract energy from a black hole's rotation through a method like the Penrose process. If a Type 2 civilization were to extend its reach to these non-stellar energy sources, its mastery over energy would become even more absolute. But even a civilization as grand as a Type 2 is just one step on the cosmic ladder. The next level, a Type 3 or galactic civilization, exists on a scale that is truly beyond our comprehension. What would a Type 3 civilization, capable of controlling the energy of an entire galaxy, to be like? And if such a civilization really exists, would we even be able to find it? In the next chapter, we will delve into the nature of a Type 3 civilization and the mysteries that surround it. The future of a Type 3 civilization ruling the galaxy. At last, we reach the final stage of the Kardashev scale. Type 3 civilization ruling the future of the galaxy. At the highest end of the scale, we find the Type 3 civilization, a galactic civilization. This stage of civilization exists in a realm that challenges even our most imaginative science fiction. A Type 3 civilization is defined by its ability to utilize all of the energy available within a single galaxy. Our own Milky Way galaxy contains roughly 200 billion stars, and a civilization at the Type 3 level would possess the power to draw energy from every single one of those colossal stars. The very thought of a civilization that spans an entire galaxy is overwhelming. But let's try to explore what that might look like as best we can. First, when considering their energy sources, the power of individual stars would be a given for a Type 3 civilization. It's possible they would deploy Type 2-style megastructures, like Dyson swarms, around every star in the galaxy, effectively turning the entire galaxy into a power plant. Furthermore, they might even harness the energy of the supermassive black hole at the galactic center. At the heart of our Milky Way, there is a black hole millions of times more massive than our Sun. They might be harvesting the energy released by the high-temperature gas in the accretion disk surrounding the black hole, or extracting its rotational energy through highly advanced methods. At this stage, the distinction between a star and a black hole might become meaningless. They would be able to control any and all celestial phenomena within the galaxy at will. That is the perspective on energy for a Type 3 civilization. We also have to touch on their methods of communication and transportation. A galaxy is vast, with our own measuring 100,000 light-years in diameter. If a Type 3 civilization operates cohesively on a galactic scale, it must exchange information and materials between stars that are incredibly far apart. However, according to our current understanding of physics, no information or object can travel faster than the speed of light. This means communication between opposite ends of the galaxy would take tens of thousands of years, a major obstacle to maintaining a unified civilization. One possibility is that a Type 3 civilization has discovered new physical laws that allow for superluminal communication and travel. For instance, technologies that are purely theoretical for us, like wormhole shortcuts through space-time, or communication methods that apply quantum entanglement, might be practically implemented by them. It would be difficult for them to function efficiently as a galactic civilization without the means to converse instantly with the other side of the galaxy. Furthermore, by the time a civilization reaches Type 3, the very concept of a single species might have changed. Even if we assume humanity could develop that far, some predict we would have likely shed our biological bodies in favor of mechanization or digitalization to explore every corner of the galaxy and manage its energy. Artificial intelligence and robots, which can operate semi-permanently, are far more suitable than fragile, short-lived biological beings, perhaps the descendants of humanity, or their AI successors, would have uploaded their consciousness to a computer and exist on a galactic network. As you can see, by the time a Type 3 civilization emerges, the very nature of what a civilization is could have transformed into something entirely different from what we know. So, if such a civilization existed in our galaxy, would we be able to find it? This question leads us to the famous Fermi paradox. The Fermi paradox asks why, if there should be many extraterrestrial intelligent life forms in the universe, we have yet to discover any trace of them. A Type 3 civilization, operating on a galactic scale, should leave traces that are observable. For example, if the entire galaxy were being artificially modified, or if unusual radiation were emanating from it, our astronomical observations might be able to detect it. However, at this moment, there is no clear evidence of any galactic-scale civilization. A study in 2015 that analyzed infrared data from hundreds of thousands of nearby galaxies reported that no signs of Type 3 civilizations were detected in any of them. This could be interpreted as evidence that such advanced galactic civilizations simply do not exist. But it's too early to draw that conclusion. A frequently discussed answer to the Fermi paradox is the Great Filter hypothesis. This is the idea that intelligent civilizations are not abundant in the universe because there is a filter somewhere along the path of development that causes most of them to go extinct. There are various theories about whether this filter lies in our future, before we reach Type 1, or in our past. During the transition from early life to intelligent beings, but it remains a leading hypothesis to explain the absence of Type 3 civilizations. For example, scenarios like self-destruction through nuclear war or environmental collapse being eliminated by AI, or being reset by a major catastrophe are all considered possibilities. Conversely, even if other civilizations do exist, they might be deliberately hiding themselves from us. This is known as the zoo hypothesis, or the idea of a self-concealing civilization. A civilization advanced enough to reach Type 3 could easily detect our existence, but might choose not to make contact. There is also the hypothesis that highly advanced civilizations may choose internal development over physical expansion. For instance, a civilization might build a self-contained society within a virtual reality and cease to interfere with the outside universe. In that case, even if a super civilization existed within our galaxy, we wouldn't be able to see it from the outside. Thus, while the existence of Type 3 civilizations is a fascinating topic, it remains in the realm of speculation for now. What is certain is that reaching the level of a Type 3 civilization involves surmounting incredible hurdles, both technologically and over immense timescales. Will humanity ever be able to reach that stage? Or will we find ourselves at a dead end along the way? In the next chapter, we will consider the limits and possibilities of civilizational development from both a technical and philosophical perspective. Limits and possibilities. We have painted a grand vision of the future. From Type 1 to 3, limitations and possibilities. At the same time, however, a fundamental question arises. Can we truly reach that far? The development of civilization is subject to the limitations of physical laws and social and philosophical constraints, which may act as walls that define our future. In this chapter, we will explore the limiting factors that lie in the path of human civilization's evolution, as well as the possibilities that still remain. First, let's consider the technical and physical limitations. The greatest of these is arguably the law of increasing entropy, exemplified by the second law of thermodynamics. No matter how advanced our technology becomes, we can never utilize energy with 100% efficiency. A portion will inevitably be released as waste heat. This fact means that as civilization expands on a massive scale, the thermal load on the environment will increase. For example, if we were to consume energy equivalent to a Type 1 civilization on Earth, most of that vast energy would eventually turn into heat, warming the planet. Even if we generate power cleanly with renewable energy, it would be pointless if the final heat output destroys the global environment. In fact, some estimates suggest that if humanity were to approach even a few % of the Type 1 level, the anthropogenic heat alone could trigger a rise in global temperatures. The very act of using energy on a massive scale becomes a risk to the environment. This problem would become even more severe for Type 2 and Type 3 civilizations, where heat dissipation could become a bottleneck for their very survival. One of the reasons suggested for the absence of Type 3 civilizations is the lack of any conspicuous signs of such massive heat signatures anywhere we look. Another physical limitation is the speed of light barrier. As mentioned in the previous chapter, according to the theory of relativity, faster than light travel and information transfer are impossible. Traversing the vastness of space would simply take too long under our current understanding of physics. Even if humanity were to journey to other star systems in the future, it would require decades or even centuries, at the very least. To cross from one end of the galaxy to the other would take tens of thousands of years. This barrier of distance and time makes the unified development of a civilization difficult and could lead to a situation where a civilization that expands too far loses its cohesion. It's possible that a civilization that grows beyond a certain size might fragment and become autonomous, ceasing to grow on a larger scale. Next, let's turn our attention to social and philosophical limitations. Even if technology advances, civilization cannot be sustained unless the human issues of wielding that technology are resolved. For instance, humanity has a long history of using technology for war and destruction. Nuclear weapons are a prime example. We already possess the means to annihilate ourselves. Carl Sagan referred to modern humanity as being in a state of technological adolescence, an immature stage fraught with the possibility of self-destruction. To highlight this danger, the more advanced the energy we obtain, the greater our power to destroy ourselves with it. New technologies like runaway artificial intelligence, biological weapons, and nanotechnology also come with unknown risks. There is also the concern that technological progress can create social disparities. If a select few were to monopolize new energy sources and advanced technologies, the world could become divided, making cooperation impossible. Ethical questions also arise. For example, ideas like covering an entire planet with solar panels or strip mining the resources of other planets would likely face a clash of values, with people questioning whether we have the right to manipulate nature to such an extent. It's not a given that all of humanity will march in lockstep, cheering for the advancement of civilization. There will be movements to apply the brakes from within, and there will be instances where greed and irrationality hinder sound development. Considering all this, a paradox emerges. Is it not more likely that humanity will destroy itself before it fully evolves? Unfortunately, we cannot say this possibility is zero. A critical answer to the Fermi paradox is that most intelligent civilizations in the universe end up self-destructing. We ourselves, in the 21st century, have faced the crises of nuclear war and climate change multiple times. If we fail to learn reason and cooperation, we may find it difficult to even maintain our current status, let alone reach Type 1. While the limitations seem to loom large, possibilities exist alongside them. Humanity has repeatedly defied pessimistic predictions and survived. Science and technology have also undergone exponential development, and things that were mere fantasies 50 years ago are now part of our daily lives. From an era when sending a person to the moon was considered impossible, we now, only about 60 years later, have our sights set on colonizing Mars. If we reach a dramatic turning point, a technological singularity, our energy problems could be completely transformed. For instance, if we were to discover new physical laws, such as quantum gravity or higher dimensional theories, and from them derive limitless energy or warp propulsion, the upper limits of the Kardashev scale would be pushed significantly higher. While it may seem like science fiction now, we cannot deny the possibility that humanity 1,000 years from now will have a completely new understanding of energy. And above all, humanity has the ability to learn and adapt, just as we are beginning to shift our energy systems in the face of climate change. Our strength lies in our ability to use crises as a springboard to change our behavior. As the likelihood of us being a lone intelligent species in the cosmos increases, a sense of responsibility may awaken within us, a realization that it is up to us to spread the flame of life throughout the universe. At that moment, humanity might overcome its internal conflicts and resolve to journey to the stars as one, even if a Type 3 civilization is far beyond our reach. The benefits gained on the path to Type 1 or 2 are immeasurable. Solving the energy crisis, achieving super longevity, coexisting with AI, pioneering other planets. Each step of this process will grant humanity a new perspective and a better chance of survival. Limitations and possibilities are two sides of the same coin. How far we can evolve depends on us. And at the same time, it depends on how far we wish to go. The future envisioned by the Kardashev scale is by no means a predetermined destiny. It is merely one what-if scenario. So, finally, using this scale as our guide, how should we envision our future? Where are we headed? As we look at the Kardashev scale, where are we headed? We can dream grand dreams about the future of human civilization. At the same time, this also serves as a mirror, highlighting the challenges we face today. The energy problem for a Type 1 civilization, the technological challenges for a Type 2, and the philosophical questions for a Type 3. Everything we've considered in this video boils down to one point: what will humanity choose? And what will it achieve from here on out? If we are to use this scale as a ruler for predicting the future, it's crucial to first accurately understand our current state, around a Type 0.7, and to clearly define the goal of a Type 1. A Type 1 civilization is one that can sustainably utilize all the resources its planet possesses. We've learned that achieving this requires an energy revolution and global cooperation. Conversely, if we can accomplish these things, humanity can advance to the next stage. The Kardashev scale isn't just a fantasy. It makes us think about what becomes possible with a certain amount of energy. It would be profound to keep this scale in mind as a measure for future predictions. However, we must not forget that the amount of energy alone does not determine the value of a civilization. Although I've mixed in some speculation with little scientific basis, the maturity of a civilization also has unquantifiable aspects, such as ethics, wisdom, art, and happiness. For instance, even if we reach Type 1 on the Kardashev scale, if that society lacks smiles and peace, it couldn't be called mature. On the other hand, if humanity can find a way to maintain harmony and prosper indefinitely, even with our current energy consumption, that in itself is an ideal. The Kardashev scale is a method of envisioning the future from the single perspective of energy, but the actual future should be much more multifaceted. Finally, as we've looked at the grand possibilities and challenges of cosmic civilizations, what level of civilization do you think humanity can reach? Should we be content with Type 1? Or should we boldly aim for Type 2 and 3? Or perhaps there's a completely different direction for our evolution? I encourage you to ponder this question and let your imagination roam. The future of the universe is a blank canvas, and it is none other than us, humanity, who will paint it. Thank you for watching to the very end. If you found this video interesting, please be sure to subscribe and give it a thumbs up. Also, our channel, Cosmic Lab, has been able to grow steadily thanks to the support of all our viewers. Thank you so much for your constant encouragement. We have set a challenging goal of reaching 100,000 subscribers by the end of 2025, and we are working our hardest on creating videos every day. If you haven't subscribed yet, we would be grateful if you would subscribe and continue to support us. Well then, we look forward to seeing you in the next video.